Okay, so let's go ahead and get started. I'm putting both the agenda in the chat and also our notes for today. So this is like what I'm going to be marking up in case you want to like follow along at home or like try the examples before I get to them to see if you can kind of stuff. So for today, announcements. Not too much. So this week we do have some new outcomes coming on this week. So our last fundamental outcome, F8, so that's very exciting, and G20 to G22. The second drop deadline for the semester and the final drop deadline is this week on Thursday. So if you have any questions about that, let me know. And otherwise, just a normal week. Oh, I can put the class notes link in here as well. Try to. There. Okay, so I'm going to share my screen and we'll go over some perusal questions and also just like some examples, especially for the inequalities. I think it's important to just sort of see some examples of how that works. So here we go. So solving quadratic equations. So as some of you guys noted, right, we've seen a lot of this before. We've already been doing this like from the very beginning of the semester, right? We have a quadratic equation, set it equal to 0. We're trying to find the roots or the zeros, the x values that you plug in that give you 0. And I think people were sort of taken aback by this sort of nasty looking formula here at the beginning. And it's just, what they've done is they've taken our like usual ax squared plus bx plus c equals 0, and they've sort of rewritten it. It's the same thing, it's just rewritten in a different format, where this p and the q, and they pull the a out so that there's no non-one coefficient in front of the x, so they sort of pull that out, and then they're finding the p and q values so that you can write it as what we call a binomial, which people were asking about, also something squared, and then you can use the fact that that's a square to like take the square root in order to solve something. So that's how you do this, completing the square. So it looks nasty, but again, in terms of like what's a variable and what's not. So here the x is a variable, but the a, the p, the q, and the r are all constants. They're all numbers. So here, note that x is the variable. That's what we're solving for. Solving for this, for x. But a, p, q, and r are all, I can't write, are all constants. The a is the same a. So this a is the same a as over here. These are the same. And then the other ones, the p, the q, and the r are different constants, but they're like basically come from the b and the c. So you like rewrite it. Okay, so the whole point of that is just like this format that you want to get it into to complete the square. So when you're completing the square, you actually kind of like start in a different way. So normally when we're using factoring to solve a quadratic equation, or if we want to use the quadratic formula, which we also talk about in this section, we need to get 0 on one side first. But completing the square does not work that way. So completing the square, you take the constant to the other side, and then you try to find this, or you do find this p value. So this is how you figure out what p is. You take 1/2 of your b term, and that's how you get your p. The p squared, you take p squared, and that's what you add to both sides, and that's what's going to make this thing into something squared. And then you can take the square root and then just subtract or add the thing to get the different values. So let's try to do that with these other examples that they had here. So they have. Well, these are like not really written as equations. I didn't realize that. So they're just like saying, okay, what do you need to add here? So if we have x squared minus 18x, here we're not really starting with an equation. They're just like, how do you complete the square? So you take 1/2 of minus 18, which is minus 9. You square it, which is 81. right? And then this is going to be x minus 9 squared, which you can check by foiling it out. That looks a little weird. This is x minus 9 squared, right? Which if you FOIL it out, the way this works is you have x squared, you have minus 9x plus 81, right? So that's the whole point, is that we can rewrite this thing as a binomial squared. You can do the same thing over here. But let's actually go through one where we have an equation. So here we have x squared minus 1 equals 3x. So here we want the constant term on the other side. So we need to subtract the 3x, sorry, x squared minus 3x. And then we're going to add the 1. So I did it all in one step. So we subtract the 3x, we add the 1. Then we do the same process. So you're going to take 1/2 of the middle value here. So maybe we'll do it over here on the side. So p equals 1/2 of minus 3. So this is minus 3 over 2. We square it. So p squared is 9 over 4. And we're going to add that to both sides over here. Add to both sides. So we're going to get x squared minus 3x plus 9 over 4 equals 1 plus 9 over 4. So on the left side, the whole point is that we can write this as something squared, and the thing that we're going to be using here is the p-value, this minus 3 over 2. So this should be equal to x minus 3 over 2 squared. And on the right side, 1 is 4 over 4, 9 plus 4 is 13, so this is 13 over 4. We can just double check our step over here, so that x minus 3 over 2 squared, that means this is the same as x minus 3 over 2 times x minus 3 over 2. You can FOIL it out. This is x squared minus 3 over 2x minus another 3 over 2x plus 9 over 4, which is x squared. So minus 3 over 2 minus 3 over 2 is minus 6 over 2, which is minus 3x, which is what we want, plus 9 over 4. So this is all just like checking this step over here. We're just checking this step. But then when we get, the whole point of this is now, in order to solve this quadratic equation, we can take the square root of both sides, which gives us x minus 3 over 2 equals the square root of 13 over 4, which is the same as the square root of 13 divided by the square root of 4, which is 2. And then you can add 3 over 2. So this is x equals 3 over 2 plus the square root of 13 over 2. And of course, we actually have two solutions, right? Because the square root of 3 could be, square root of 13 could be negative also. So we could also have x equals 3 over 2 minus the square root of 13 over 2. So these are our two solutions. So completing the square is a nice way to solve your quadratic equation when you can't just factor it with nice integer values, right? So we would be very unlikely to come up with these square root of 13 over 2 values when we're just factoring it the way we learned earlier in the semester. So completing the square is one way to do that. Personally, I don't really use it because I just go straight to the quadratic formula, which will also give us the same solutions. So actually, let's maybe just do that now. Or we can use the quadratic formula. Either one is fine, whichever one you prefer. So if I'm going to use the quadratic formula, x squared minus 1 equals 3x, to solve the same problem. In this case, we're going to start the way we did with factoring, where you get 0 on one side. So this is x squared, I'm going to subtract the 3x, minus 1 equals 0. I stuck my 3x in the middle because I want to write it in this form of ax squared plus bx plus c equals 0. Right, so, and then we use the quadratic formula. So, and the quadratic formula is giving you the x values, the numbers for x, that solve this, that, you know, when I plug them into this version on the left side, I'm going to get 0. So it's solving it just like factoring it is a way to solve it. And so the quadratic formula says x is equal to negative b minus a minus 3 plus or minus, and the plus or minus is just because of the square root of b squared, which is minus 3 squared, minus 4 times a, which is just 1 in this case, and c is minus 1. The negatives are really important. So if you have a negative as part of your coefficient, you have to include that negative. And then the whole thing gets divided by 2 times the a value, which is 1. So this is our quadratic formula. X is equal to negative b plus or minus square root of b squared minus 4ac, all divided by 2 times a, and that's what we just used here. And then you just simplify that as much as you can. So x is equal to positive 3 plus or minus the square root of 9. And again, here we have minus minus, which is plus 4. So that's really important that we get those signs right, divided by 2. So this is x equals 3 plus or minus the square root of 13 over 2, which is the exact same thing we got here, which is a good sign, right? So if you're on the Friday assessment, you have extra time, you can do it both ways and check to make sure you get the same answer. But either one is fine. If you're more comfortable with one or the other, you can take your pick. Is that okay? Any questions? I think there's something. Why could it be negative? Rose, are you asking from when I said this back up here with the square root of 13? This is just that when you have a square root of a number, so it could be negative or positive. So when I take, for example, the square root of 4, I could have plus 2, or I could have minus 2, because plus 2 times plus 2 is 4, and minus 2 times minus 2 is 4. So we just want to make sure we're taking the square root. You can have both a plus or a minus. Does that answer your question? Great. So let me know if you have a follow-up. I hope that helps. Yeah, so, and the same thing with the quadratic formula, it's built in. They put in the plus or minus here. It actually means 2 solutions. You have one solution with a plus and one solution with a minus. So you give 2 different answers. Unless that b squared minus 4ac turns out to be 0, and then you actually only have one answer. Or also, if your b squared minus 4ac turns out to be negative, then you have 0 answers. Maybe let's just write that down. So note, b squared minus 4ac, this number determines how many solutions you have. How many solutions you have to the quadratic equation ax squared plus bx plus c equals 0. Namely, if b squared minus 4ac is positive, we have 2 solutions. Just like in this example that we just saw. So if you get a positive number under the square root, then you have a plus solution and you have the minus solution. So you have 2 answers. If b squared minus 4ac is straight up equal to 0, we have only one solution, because plus 0 and minus 0 is the same thing. And finally, if b squared minus 4ac is negative, we have 0 solutions, since the square root of a negative number is not a real number. Negative number is undefined. So, so if you are like, oh, am I going to find any solutions? You can do a quick check of b squared minus 4ac and say, oh, hey, how many solutions do I have? Yeah, so here are just some vocabulary. So this is just vocabulary. So these weird looking words. So it says a quadratic trinomial. So the quadratic is telling us that we have degree 2. Oops. So quadratic means degree 2. And the degree is the highest power of the variable that you see in your polynomial. And trinomial, so the tri part means 3, and the nomial is terms. So here when we have a binomial, bi means 2, and nomial is terms. And Ray looks this up, so this on the Google, which is great. So it's kind of funny to say we have 2 terms is equal to 3 terms, but it's 2 terms squared. So when you have a binomial squared like this, and then you combine like terms, you're going to end up with a trinomial, which is 3 terms on the other side. So just some vocabulary, which can sometimes be helpful. So here's our quadratic formula, which I already talked about. So, and a couple of people linked to songs. So there's a cute little ditty, a little song that you can, if you're having trouble remembering it, the song can help. So I put in some links. Sydney shared one, and I think somebody else, maybe Ariana, shared another one. I'm not sure if it's the same one, but yeah. So if you're having trouble remembering it, you can go learn the song. I think Thomas also points out once you use it a few times, it's a little easier to remember. So just practicing will also hopefully do the trick. One of our MWs said, application is always weird for me because it's always my last choice option when factoring. So I'm not sure what you mean. Maybe you're misunderstanding applications because of the way they like introduce this. So applications, they're just talking about doing a word problem essentially, like how do we apply this in process? But then they like jumped straight into what are our choices for solving a quadratic equation. So it was a little bit of a weird start to this section. But yeah, we have different possibilities. So we can factor. Sometimes, depending on how it's set up, we can extract roots or complete the square so that we can extract roots, or we can use the quadratic formula. Some people just say, hey, the quadratic formula always works. I'm not even going to bother trying all these other things. I'm just going to jump straight to the quadratic formula. So that's one option. The quadratic formula, personally, what I do is I try factoring first, and then I jump to the quadratic formula. So me, Becky, I try factoring first. And then go straight to the quadratic formula. But if you prefer completing the square, you can do that, whatever you want to do. You can jump straight to the quadratic formula. I find factoring, if you can do it, is easier. And also the quadratic formula, it can be a little bit tricky to go back to the factored version, particularly if you have fractions. So I personally would recommend, if you can factor it, do that as much as possible, because the factoring is going to be better when you're not solving an equation, like you need it in other situations anyway, so, or it has like other uses as well. So I recommend factoring if you can, quadratic formula if you can, or completing the square if you prefer that. Yeah, so Bridget, which method to use? There's kind of, to some extent, there's also like a little bit of some intuition that you can develop, like when you practice more and more, and you're like, you can kind of look ahead a little bit. Another thing that you can do is if you're like having trouble factoring, so tip, if you're having trouble factoring and you're thinking, oh, maybe I have to use the quadratic formula. Do I have to? Can I factor this with integers or not? You can compute b squared minus 4ac if this is a perfect square. Something that you can take the square root of, then you should be able to factor it with integers. Can factor with integers. But if in like the example above, you compute b squared minus 4ac and it's 13, you're like, oh, I'm going to get a square root of 13 in here. I'm not going to be able to factor this with integers, so I might as well just use the quadratic formula or completing the square. So that's a way you can kind of like check And if you're like, oh, it is an integer, then you can like see like, oh, this is what I'm gonna have. I can do the factoring if I want. So here's an application, a word problem, right? Where we can like set this thing up and use these skills. So this, and people wanted to go over it and asked if we will see questions like this on the Friday assessment. Yes, so we have outcome G27, which is not coming on quite yet, which will be on a little bit later. And that one asks us to set up a mathematical model, which is what we're doing here. We're like, okay, we have this real life situation and we want a mathematical formula that's going to model this situation for us based on, you know, some kind of geometry or some kind of situation like this. So I'm going to make this a little smaller so we have some more space. So this one says the owners of a daycare center plan to enclose a divided play area. They kindly drew us a picture. So they're going to have this play area. They're going to divide it in two. Maybe they're going to put some kids on one side and some on the other. And it's going to be up against the back wall of their building. And so what they're saying is we're going to need fence to go around the outside and also fence for the middle dividing part, but we don't need fence over here against the wall. So that's what we're trying to do. We have 300 feet of total picket fence that we can use, and we want the area of the playground to be 6,000 square feet. So we have something about the fence that we're using, and that's like going along the edges. So that's talking about perimeter. And then the area, right, is length times width for each of these pieces. So can they enclose the playground with the fence they have? And if so, what should the dimensions of the playground be? So we want to think about these two different pieces of information that we have. So then we know the area is equal to 6,000 square feet, and that's equal to like the length times the width, whatever those are. Let's call it length and width, which we're going to call X because that's how they labeled it in the picture. So this is equal to L times X. And we know that, so we have the area and we have 300 feet of picket fence, which is going to be equal to our perimeter is equal to 300 feet of picket fence. And so we need to figure out how much do we have here. So if the width over here is X, right, that means we need fence for this part and for this part and for this part. So that's X plus X plus X. That's the 300 plus this other part up here, which is our length plus the length. Right, so we have that 300, not 3,000, is equal to 3x's plus whatever that length variable is, right? And so we have two equations here. We have the perimeter, which tells us that 300 is equal to 3x plus whatever that length is, and the area, which is telling us that 6,000 is equal to L times X. And so what we can do with this is we can take one equation, our perimeter, and say, okay, I can solve for L. So 300 minus 3x is equal to whatever that length is. And then I can plug that into my area formula. So plug in to area formula. So we have 6,000 is equal to the length multiplied by the width, which is x. But we know that the length is 300 minus 3x. Is equal to this length. So we can plug in 6,000 is equal to 300 minus 3x multiplied by x. And now we can, distribute this. So this is 6,000 equals 300x minus 3x squared. We want to get 0 on one side. Me personally, I want my x squared term to be positive because it just makes life a little bit easier when you're solving these. So what I'm going to do is add my 3x squared over to this side and subtract my 300x so that I can make this positive. So I'm going to add 3x squared. I'm going to subtract 300x because that one was positive. I still have plus 6,000 on my left side equal to 0. And then to solve this, the next thing I would do is divide everything by 3 because 3 goes in evenly, so divide everything by 3. X squared minus 100x plus 2000 equals 0. And then I'm guessing probably we can't factor this because we're in the quadratic formula section. So we would do x equals negative b, so that's negative a negative 100 plus or minus the square root of b squared minus 100 squared minus 4 times 1 times 2000 divided by 2 times a, which is 1. Oh, I'm running out of space. This is terrible. Let's move this over a little bit. And then come up here. So this is x equals positive 100 plus or minus the square root of 100 squared, 100, 0, 0, minus 8,000 times 4,000 divided by 2. So x is equal to 100 plus or minus the square root of 10,000 minus 8,000 is 2,000 divided by 2. Okay, so if you were in a Friday assessment, we can't really do too much more with this. You can just leave it for your Friday assessment. If you're home doing your homework, you can plug that into a calculator and get some numerical approximation if you want. But the hard part is usually doing this setup and figuring this out. So you really want to, as always with a word problem, like put yourself in that situation. You're like, I have this much fence. How am I going to figure this out? Right. So we really want to think about it, answer the question as much as possible, set up our different things that we know some information about. Sometimes we'll have to like plug one into the other one. Any questions on this guy? Okay. We had a request to go over this example, which said solve 2x squared plus kx plus k squared equals 1 for x in terms of k. So this is about keeping track of everything. So you can use the quadratic formula on this also. And we have to pay attention to what's a constant. So k is just some constant. X is the variable that we're trying to solve for. So this is, we always have to get 0 on one side. So we have 2x squared plus kx plus k squared minus 1 equals 0. And then the trick here is to be careful about what's what. So this 2, that's our a in our quadratic formula. The k is our b. And then the tricky part here is that c is equal to k squared minus 1, whatever that number is. And then you just plug it into the quadratic formula. So use the quadratic formula. So x is equal to negative b, so minus k, plus or minus square root of b squared, so that's k squared, minus 4 times a, which is 2, times c, which is k squared minus 1. All divided by 2 times a, which is 2 times 2. So x is equal to minus k, we can maybe simplify this a little bit, plus or minus the square root of k squared, minus, so here we have to distribute. So this is minus 8 times k squared, minus 8k squared. But then we also have minus 8 times minus 1, so that's plus 8 divided by 4. So x is equal to minus k plus or minus square root of minus 7k squared plus 8 divided by 4. So if you, have your k value, you can plug it in and solve for x. That's what you've done. You've solved for x in terms of k. Any follow-up questions on that guy? Okay. So then we have quadratic inequalities, and actually for us, we're going to go beyond just quadratic inequalities. So if you have just a quadratic inequality, you can solve it graphically, which is really nice. It's nice to see that. If it's more than just quadratic, we're going to be dealing with cubics, for example, maybe even some quartics, degree 4, and rational inequalities as well. So where you have a rational expression with a less than or equal to or greater than or equal to. So inequalities are harder for most people, and they are definitely more work than just solving an equation, because as part of solving your inequality, you have to go solve the corresponding equation, but then you have more work to do. So when you solve the equation, you're not just done. There's more work to do for an inequality, and you have to pay attention. So, and that should make sense that it's harder, right? When you're solving an equation, you're saying, what are the numbers that make this exactly equal? With an inequality, you're like, I need to find all the numbers that make this bigger or smaller. So sometimes it jumps this thing around. Okay, so let's just go through some examples first. So there are a couple of things here. So here, when we have, I think what order I want to do this. So here we have, actually, before we even get to quadratic, so quadratic means degree 2. Degree 2. We'll actually do more than this. We'll do more than just degree 2. So we're going to get more complicated. And in fact, this first one is linear. It's not degree 2. It's just degree 1. Linear, degree 1. Right? Because there's no x squared in here. And even though it looks nasty because there are fractions, they're just numerical fractions, which are not nearly as nasty as the ones where you have an x in the denominator. So also note that this is, we have numbers, but no variables in the denominator. But no variables in the denominators. So denominators, I don't know how to spell it. So when I'm solving this, the first things that with a degree 1, I'm just going to combine like terms. So here I have a minus 1/3 x, and here I have an x. And for the most part, with a degree 1 inequality, you can treat it the same as an equation with one big exception. So for degree 1, can mostly treat like an equation, except the big exception, we can't, maybe I should say this. If you multiply or divide by a negative number, you have to flip the inequality. So let's do this example. So if I'm doing this example, I'm going to try to avoid having to do that so I don't make a mistake. So what I'm going to do for, so I have a minus 1/3 x and I have an x. So I'm going to add 1/3 x to both sides. That's fine. Adding and subtracting works the same way as it does for equations. So when I do that, I get minus 4 is greater than or equal to x plus 1/3 x. So that's 3/3 of x plus 1x. So this is, you still have the 1/4, and then we have plus 4/3 x. All right, so that's 1x plus 1/3 x. And now I'm going to get my 1/4 to the other side. So I'm going to subtract my 1/4 on both sides. Minus 1/4, minus 1/4. So, oops. Do that now, maybe I will. So this is minus 4 minus 1/4 is greater than or equal to 4/3 times x. So -4, so that's the same as -16/4 minus 1/4. So I have on the left side, -17/4 is greater than or equal to 4/3 x. And I need to get my x by itself, so I'll multiply both sides by 3/4. So I have x is less than or equal to -17/4. And again, I multiply both sides by 3/4 to get rid of the 4/3. And so x is less than or equal to -17 times 3, that's -30, -21, -51/16, I think. So any number that's smaller than or equal to -51/16, if I plug it in up here, will give me left side is greater than or equal to the right side. So I have infinitely many solutions to this inequality, which is normal for inequalities. I'm going to why do we have to, so let's maybe do the same thing in a different way. So one of the things that's tricky is that sometimes you have multiple options for how you want to do this. Let's do it another way. So I'm just going to do it again, but in a different way. So this is, copy it. So I'm going to do the same problem in a different way. Same problem. Variation on the solution. So if you're like me, you say, oh, hey, fractions, that's terrible. Let's get rid of our fractions, okay? So I'm like, okay, I have a denominator of 3 and a denominator of 4. So if I multiply both sides by 12, I'm gonna get rid of my denominators. So I'm just gonna multiply both sides by 12. Since 12 is positive, I don't have to worry about flipping the inequality. I do have to distribute across, right? So 12 times the -1/3 x is going to give me -4x. -4 times 12 is -48. This is also nice because we'll check my work and see if I did it correctly over there. And 12 times 1/4 is 3, plus 12 times x. And now this time, let's say I didn't notice, right? So I would normally, if I'm doing this problem, I'm sort of reading ahead and looking ahead and saying, okay, I'm going to add my 4x to this side to keep my x value positive. But let's say I didn't notice and I instead decided to subtract 12x to get my x's over on the left side. And I will also add 48 to both sides. And so here I'm going to do -12 minus 14, so that's -16x is greater than or equal to, now I've added 48 to both sides, and that's greater than or equal to 51. This is looking good for matching my previous solution. And now in order to get x alone, I have to divide by -16. But when I divide by -16, I have to flip the inequality. So I'm going to divide both sides by -16. And I have to flip the inequality. X is now less than or equal to -51/16. So here we are divide by a negative number. Means, so we need to flip the inequality. Right, so I mean that the greater than or equal to became a less than or equal to with these things on the same side. And then notice that this solution here that we got down here is the same as our solution up here because the x is the smaller side. So this is like, I don't know if you guys learned about inequalities when you were a kid. We learned the shark mouth opens to the bigger plate of cookies. I don't know why the sharks are eating cookies, but anyway, the smaller side you have less cookies, right? So the bigger side, you have more cookies. Here we have negative cookies, so nobody wins anyway. But x is the smaller side than 51/16. So this expression up here is the exact same thing. X is on the other side, so but the smaller side is the x side. Smaller side is the x side. Why do we have to flip the inequality? So notice if I did not flip the inequality, I would have gotten the wrong answer. I would have said x is bigger than minus 51/16. You have to flip that inequality. Why do you have to flip the inequality? Let's put this down again. Why do we flip the inequality? So here's what happens. So I think I'm going to put this up on a number line. Here's 0, here's 2, and here's 4. So I think we can all agree that 2 is less than 4, right? If I multiply by a positive number, like 3, multiply by positive 3, I get 6 is less than 12, right? So they get bigger. I go up to 6, and my 4 goes up to 12, right? And so still, 6 is less than 12. They maintain that same relationship. But if I multiply by a negative number, like -3, then they go down, right? 2 goes down to -6, and 4 goes to -12. And -12 is less than -6. Maybe I should go the other way. -6 is bigger than -12, right? Or -6, -12 is less than -6, or you can write it the other way. -12 is less than -6. So here, when we multiply by -3 on this thing, you have to flip the inequality because they change their relationship to each other, because -12, the absolute value of it is bigger, but -12 is a smaller number than -6, right? If you owe $12, right, you're more in debt than if you owe -6. Okay, so that's what happens with our inequalities there. Let's take a 5-minute break now. Let's come back 10:48, and I'm going to go through some more examples before we go into breakout rooms, just because I think the inequalities in particular need some more examples. So let's take a 5-minute break, come back at 10:48. We will. So what we're going to do now is we're going to do some more inequalities that are not necessarily even quadratic. And so if they're quadratic, like the book shows, you can follow along with the graphical solutions. And if they're not quadratic, it becomes harder and harder to solve them graphically. And so we want an algebraic way of solving them. So same thing, we're solving the inequality, which means we're trying to find the x values that make this inequality true, that make the left side greater than or equal to the right side. So again, we're solving the inequality, which means, i.e., we're trying to find the x values that make this true, i.e., that make the left side bigger than the right side. It's technically greater than or equal to the right side. So that's what we're trying to do. And when we solve these inequalities, the first step is to go back and solve it the same way we solved, to put in an equal sign and solve the equation the same way we did before. So the first step is to solve the corresponding equation. Solve the corresponding equation, i.e., replace your inequality with an equality. And the reason we're doing this is because the equality will give us the x values that make the sort of corresponding function equal to 0, and testing whether something is, finding the zeros is much easier than testing whether something is positive or negative, or maybe we're going to get 0 on one side like we did before, because testing whether something is positive or negative is easier than finding whether one thing's bigger than something else. So we want to find whether something's positive or negative. So we're going to do the same thing. We're going to get 0 on one side and solve it. I'm going to keep my highest degree term over here because I want that to be positive, just because it makes things a little bit easier. So I'm going to subtract 3x from both sides. 2x cubed minus x squared minus 3x equals 0. We're going to try to factor this as best we can. The first step of factoring is always pull out a common term. So we have x times 2x squared minus x minus 3 equals 0. Now we want to factor the inside part. So we still have this x. It's important that we do not lose the x over here. And then we're going to factor this. So you can use your factor by grouping or whatever you're doing for your factoring. I honestly just kind of do a guess and check. So x, I'm going to guess we have minus 3 and plus 1 and then check it. So 2x squared minus 3 plus x plus 2 is minus 1 and minus 3. So this is right. We use our good old zero factor principle. So we get 3 solutions to the equation part of this. So we get x equals 0. Again, this is really important that we don't lose that third solution here. We have 2x minus 3 equals 0. So this is the same as 2x equals 3, or x equals 3 halves. And then we have x equals minus 1, or x plus 1 equals 0. So x equals minus 1. Okay, so what is this telling us? These are the 3 places where this function, 2x cubed minus x squared minus 3x, actually hits the x-axis, right? This is where it's equal to 0. And so what happens is these are the only places where it's equal to 0. And so for an inequality, we're trying to figure out, we're trying to solve this corresponding inequality. So we want to solve this inequality, right? Which is the same, actually I'm going to go over here, is the same as 2x cubed minus x squared minus 3x is greater than or equal to 0. So solving the original inequality is the same as solving this. So we're trying to figure out where this 2x cubed minus x squared minus 3x is positive. Where is it greater than or equal to 0? We already know where it's equal to 0. We just found those 3 values. But those are the places where it can cross the x-axis. So everything before that first value, x equals minus 1, all of those values are either positive or they're all negative. And so what we're going to do is we're going to set up a, we're going to do something called sign analysis. So this is step 2, is sign analysis. And what does that mean? It means we're analyzing the sign, i.e. the plus or minus, whether it's positive or negative. So analyze the sign, which is plus or minus. Plus or minus. And so what we're going to do is we're going to set up a number line and we're going to mark off these points. So from left to right, we have minus 1, then we have 0, and then maybe I don't want to mark 1, I want to mark 3 halves. Oops. 3 halves is over here, bigger than 1. Okay, and I'm going to I'm going to draw some lines down because we have, what we do is we have 3 regions. So we have this region where x is less than minus 1. I'm going to label these up here. So this region here is x is less than minus 1. We have x is actually equal to minus 1. Then between minus 1 and 0, the way we describe this is minus 1 is less than x is less than 0. So this is x values that are smaller than 0 and bigger than minus 1. And then we have a third region where 0 is less than x is less than 3 halves. And then we have a fourth region, color. Fourth region where x is bigger than 3 halves. And what we want to do is we want to test one X value in each of those regions. So over here in the first region, I can test something like X equals -2. And if when I plug in -2, I get a positive number, then that means any value that's less than -1 is also going to give me a positive number. If I get a negative number, any value that's less than -1 will also be negative. So I'm going to plug this in to here. So I'm going to plug it into this thing. 2 times -2 cubed minus -2 squared minus 3 times -2. Ugh. What is that equal to? Actually, I don't care. I don't want to know what that's equal to. So instead, I'm going to look at the factored version of this. So I'm going to look at, I don't have enough space. Use the factored version, which is x times 2x minus 3 times x plus 1. Why do I want to use this? Because I only care about whether it's positive or negative. I don't care what the actual number is. And so, yes, you can go and compute this. I'm probably going to make a mistake. So I find it easier to say instead, I'm going to look at x, that's just -2. Then I have 2 times -2 minus 3. And then I have -2 plus 1. So -2, that's a negative number. I'm multiplying that by -4 minus 3 minus 7. That's another negative number. And then I multiply by -2 plus 1, which is another negative number. So negative times negative is positive, times another negative is negative. So that means that this whole region, for all the x values that are less than -1, that these values are going to be negative. So they are not solutions to our inequality. When I do the same thing between -1 and 0, I can test something in between, maybe -1/2. Test x equals -1/2. It's really squishy, but I'm going to use this same factored version. So I have -1/2 times -1/2. Oh, it's so small. 2 times -1/2 plus -3. Oh no. Maybe I can make it bigger. This is terrible. -1/2 times 2 times -1/2 minus 3 multiplied by -1/2 plus 1. It's too squishy. -1/2 is negative. 2 times -1/2 is -1 minus 3. That's also negative. But -1/2 plus 1 is +1/2, so that's positive. And negative times positive is a positive number. So these ones will be solutions. These x values will give us a positive value in there. Now I can do my next region, test something in here. This one's a little easier. I can test x equals 1 because that's in between 0 and 3/2. So I have, again, I'm plugging it into my factored version of the formula over here. So I have 1 times 2 times 1 minus 3 times 1 plus 1. So this is a positive number. 2 minus 3 is still negative. Last number is positive. So this is a negative number. So these are not solutions. And then finally, I'm going to test something bigger than 3/2. Maybe x equals 2. So I have 2 times 2 minus 3 times 2 plus 1. So this is positive multiplied by a positive number multiplied by a positive number gives me a positive number. So these are also solutions to our inequality. And so our final solution So the solution is -1 less than x less than 0. Maybe I should really say x values in x values, -1 less than x less than 0, and x values that are bigger than 3/2. In interval notation, -1, oh, actually, I'm going to change this a little bit. We need -1 less than or equal to, because when we plug those numbers in, we get equal to 0, and equal to 0 should be part of our solution. So we have -1, and that's going to give us a square bracket over here. -1 to 0, union 3/2, and then you can go forever and ever and ever in the positive direction. So this is our answer. Any x values between -1 and 0 will solve our inequality, and any x values that are bigger than or equal to 3/2 will solve our inequality.
I'm still confused though. Like the first x is less than -1. So when that is a negative, how is that not okay again?
So what happens is we're plugging in an x value that's less than -1. And the question is the corresponding y value positive or negative? So what's happened is we've figured out that for this formula, if we were to graph this equation of y equals 2x cubed minus x squared minus 3x, so if we graph y equals 2x cubed minus x squared minus 3x, we know where the zeros are. The places where it's equal to 0, we found are x equals 0, x equals 3/2, and x equals -1. So if we were to graph this, we know that at -1, it's going to go through the x-axis. It's going to go through the x-axis at 0, and here's 1, and here's 2, and here's 3/2. It's going to go through the x-axis at 3/2. And when we're doing sign analysis, what we did is we said, okay, if I plugged in a smaller number than x equals -1, something like x equals -2, I get a negative number. And that means on my graph down here that all these values are going to be negative. I don't really know what it looks like too much, but they're going to be negative numbers. They're below the y-axis. And then I plugged in an x value that was between -1 and 0, like -1/2, and I got a positive number. So down on my graph, I'm getting positive numbers between -1 and 0. And then I plugged in x equals +1, and I found it was negative. So that means I'm getting negative numbers between 0 and 3/2. And then finally, I plugged in x equals 2, which is bigger than 3/2, and I got positive numbers out. And so because we want to know where is this thing greater than or equal to 0, where is it either positive or equal to 0, that means our solutions are where the x values, where the y values are positive. So the green are our solutions. And these are the x values between -1 and 0 is where the y value is positive. And x values bigger than or equal to 3/2 are where the y values are positive. I know it's confusing.
All right, I got it. That clarifies it a lot.
Yeah. As you're doing more and more of these problems, you're probably going to notice that often they switch minus plus minus plus or plus minus plus minus. Often that happens, but not always. So we have to be a little bit careful if you're noticing that they're not switching, you might want to double check, see what's going on there. We'll talk more about it as we look at more examples. Most of the time it'll go back and forth, but not always. So you do have to be careful. Okay. I do have more examples to go over, but I want to instead switch over to our breakout room so that we have a chance to do our FA review, and then you can practice a little bit. So the Jamboard does have some inequalities and also some other problems on there that you guys can practice. And then maybe while you're working on that, I'll just talk through the other examples and record it so you can go back and watch them later, if that helps. Okay. And also always feel free to call me in and ask questions. And I know like sometimes on the FA reviews, when I'm like, do you still have any questions? And people are like, oh, I don't understand transformations of graphs or difference quotients or something. That's great. But also you can call me into the breakout room and I'm happy to go over things with you guys there as well. Okay, I'm gonna put us into breakout rooms and let you guys do, let me just throw our agenda in the chat one more time in case you didn't get it earlier. So you can find the links to the Jamboards and all that. Okay, let's do breakout rooms. Okay, guys, so while you're in your breakout rooms doing your Friday assessment review, I'm going to go through a few more problems. So they've given us some steps to solve a quadratic inequality. And they're talking about using a graph, which is a little easier to do with quadratic inequalities, but we're going to do it algebraically with some more complicated things. And then I just wanted to note, so there were some comments like, oh, we replaced the equal sign with the inequality sign. We solve it the same way as we do equalities. That's like, you have to do that as part of it, but not, that's not everything. So this is how we start. But then we'll have more work. Especially for inequalities in general, right? If you just have a quadratic, you can think about what the graph will look like and use that to solve your inequality. And if you have something more complicated, then you might have more algebraic work to do as well. So let's go through a couple more examples. So here's another one, very similar to our last one, except here we're going to see a case where it doesn't bounce back and forth plus minus, where sometimes that breakpoint does not actually mean that you're switching signs. So here, again, our step one is solve the equality. Right, so equality where it's equal to 0. So x cubed minus 6x squared plus 9x equals 0. Again, in this case, we have a factor of x in each term, so we can pull that out. X times x squared minus 6x plus 9 equals 0. And then we factor the x squared minus 6x plus 9. So we have x times x minus 3 times x minus 3 equals 0. So we get x equals 0. And then both of these give x equals 3 as a breakpoint. So step 2, we do our sign analysis. So again, I'm going to set up my number line. I only have 2 breakpoints. So I have x equals 0 and I have x equals 3. Just going to drop down some lines here to separate these out. So this first region is x is less than 0, or if you prefer minus infinity to 0 is another way to write it. And then our second region over here is 0 is less than x is less than 3. So these are all the numbers that are bigger than 0 and smaller than 3 in in interval notation. It's parentheses 0, 3 parentheses. And then we have a third region out here, which goes forever. So this is x is bigger than 3, all the x values that are larger than 3, or in interval notation 3 to infinity. In this case, we have what we call a strict inequality, which means there's no equals to sign here. So these values, x equals 0 and x equals 3, will not be as part of our solution set, because those are the values that when we plug them in, we'll get equals 0, but we want something that's bigger than 0. So 0 is not going to be, a y value of 0 is not part of our solutions. So we have to be careful of that in our answers. We're going to use, again, the factored version to test for the sign. So use factored version, which is x times x minus 3 times x minus 3, which we can rewrite conveniently as x times x minus 3 squared, right? And this is nice because when you square something, it's going to be positive. Right, so when I check x is less than 0, I can take any number that's less than 0 and plug it in. I'll try to keep it small, probably, x equals minus 1. So here I'm going to take x equals, using this guy, x equals minus 1, and then minus 1 minus 3 squared. So this is going to be a negative number. And then, yes, this is -4, but I'm going to square it. So it's going to be a positive number. And negative times positive is a negative number. And these are negative numbers down here. And so these are not part of our solution. So not part of our solution. That's probably not. So, not solutions. And then we're going to plug in something between 0 and 3. So I'll do x equals 1. So here again, I have x equals 1, and then I have 1 minus 3 squared. So this is positive, and then anything squared is positive. So I get a positive times positive is positive. So these values are part of our solution. So we want to include those. And then we have x bigger than 3. So if you're not paying attention, you might say, oh, minus plus, the next one's going to be negative. But let's test. So when we test, okay, so we can also test a value that's bigger than 3. You know, it can be way bigger. You can test x equals 10 if you want. Maybe that's easier. Here, again, it won't matter too much because we'll just use the factored version. So we have 10 times 10 minus 3 squared. 10 is positive. Anything squared is also positive. So positive times positive is positive. And so these are also going to be solutions because we want the numbers that are bigger than 0 or positive. So this is a situation, right, because this is what we're trying to solve. So this is a situation where it does not change sign, even though we have a breakpoint here at 3. The reason it does not change sign is because we learned this new vocabulary word, multiplicity, right? So 3 has an even multiplicity. And so you're squaring it. It behaves like y equals x squared, where it hits the x-axis, but then it bounces back off again. So our solutions for this, our answer, is 0 to 3. We're not including 3, so we use parentheses or 0, 3 to infinity. And again, the reason we're not including the 0 or the 3 is because we have this, what we call a strict inequality. So this means absolutely bigger than equal to is not okay, right? So if this was greater than or equal to, then we would use square brackets to include the 0 and the 3. So that's that example. Then we have, this example is a rational inequality. Meaning that we have an inequality but involving a rational expression where rational means polynomial divided by polynomial. So here, i.e., we have variables in the denominator. And as a huge warning, we cannot clear denominators or cross multiply for inequalities when we have variables in the denominators. Cannot clear denominators or cross multiply, which is the same thing, when we have variables in the denominators for inequalities. So this is something that's very different from the equation situation. So when you have an equal sign, you can do that as long as you make sure that your solutions are in the domain in the end. But here we cannot do that. So we have to, unfortunately, it means we're going to have to add these rational expressions together. So we would do the same thing. We're going to get 0 on one side first. So I didn't write this down before, but really a step 0, get 0 on one side, which is what we were doing in the other part as well. So we're gonna get 0 on one side. You can go in either direction. You're gonna have to subtract one thing from the other side. It doesn't matter which direction you go in as long as you're then paying attention to what's gonna happen afterwards. So I don't know which one's better. So I'm just gonna say 1 over x minus 2 over x plus 1 is less than or equal to 0. So I just subtracted the 2x plus 1 from both sides. I have this. And now we need to add these two fractions together. And we do that again by getting a common denominator. So since we have x plus 1, we don't have anything in common already. So we just have to multiply the first one by x plus 1 over x plus 1, and the second fraction by x over x to get a common denominator. So we have 1 times x plus 1 divided by x times x plus 1. So we're making our common denominator, minus 2, and this one we multiply both the top and the bottom by x, less than or equal to 0. And now that we have a common denominator, we can subtract the numerators. So we have x plus 1 minus 2x. If we had more than one term here, we would have to be careful about distributing that minus sign. We have an x times x plus 1 in the denominator is less than or equal to 0. So in the top we can combine, so we have minus 2x plus x is just minus 1x. So we have 1 minus x in the top divided by x times x plus 1 is less than or equal to 0. So now another big difference. Hi, Ariana. Okay, so here's another difference between inequalities and equalities. When you have an equal sign with a rational expression, we can basically just ignore the denominator. But here you cannot. We have to include the denominator because remember, we're trying to test whether this thing is positive or negative, whether it's less, where is it less than 0. And these x values in the denominator can affect that, right? So if this x is negative, it's going to affect whether the overall term is negative. And if it's, if this x plus 1 is negative or positive, it's going to affect whether the overall thing is negative or positive. So we have to take into account all three of these things. And so we're not, step 1, you need to find the zeros of the numerator and the denominator. And the denominator. So from the numerator, we have 1 minus x equals 0, so x equals 1. From the denominator, we have x times x plus 1 equals 0, so we get x equals 0. And we have x plus 1 equals 0, which is x equals minus 1. So these are all breakpoints for our sign analysis. Let's give myself another page here. So all three are breakpoints for sign analysis. So I'm going to set up my number line with 1, 0, and minus 1. So minus 1, 0, positive 1. Drop down some dividers. So another thing that we want to notice here is that we're going to be doing less than or equal to. So equal to 0 is okay. X equals 1 gives us something that is equal to 0. So that one will be a solution. That one, no matter what, we already found one solution. If I have x equals 1, I have a solution. I'm going to do a closed dot here to remind myself that this is a solution. This is not the case for x equals 0 and x equals minus 1 because these make the denominator 0 and you're not allowed to divide by 0. So we can have numerator equals 0 does give us a solution because of the equals sign greater than or equal to, but these ones can't. So it can be helpful if you just right away draw little open circles to remind yourself those ones are not solutions because the original function is not defined at those points. And then we're just going to do the same kind of thing, the sign analysis with these 4 different regions. So we have this first region where x is less than minus 1, or if you want, minus infinity to minus 1. We have a second region, minus 1 is less than x is less than 0, or minus 1 to 0. We have a third region, 0 is less than x is less than 1, or in interval notation, 0 to 1. And then we have this fourth region going out forever that way. X is bigger than 1, which is 1 to infinity in interval notation. Okay, so we do the same process. We're going to test a value for x that's less than minus 1. And again, we're going to use the factored version, but here we're dividing these things out. So we have, but still when you're multiplying, as long as you have it factored in both the top and the bottom, you can still use this idea where if you're multiplying or dividing by a negative, you multiply or divide the negatives. It doesn't matter what the value, actual numerical value is. So we're going to be looking at this expression 1 minus x over x times x plus 1, because this is the expression that we're comparing to 0. we want this factored version of it, we're going to test a value that's less than -1. So maybe test, x equals -2. So we have 1 minus a -2 divided by -2 times -2 plus 1. And 1 minus -2, that's positive, 1 plus 2. So you get a positive number in the top. And then we're multiplying a negative number, -2, multiplied by -2 plus 1 is also negative. So negative times negative is positive. Positive divided by positive is a positive number. But we want the negative numbers. So this is not part of our solution set. So now we're going to plug in a number between -1 and 0. So for this one, we're going to test something in between. Maybe test x equals -1/2. So when I plug this one in, we have 1 minus a -1/2. And then we have -1/2 multiplied by -1/2 plus 1. So with these fractions, you really have to be careful about what's going to be positive or negative, or it's easier to make mistakes. But here we have 1 minus a negative number, so it's 1 plus 1/2. So we have a positive number in the top. Divide by -1/2 is a negative number, multiplied by -1/2 plus 1. So 1 is bigger, and that's the positive one, so we get a positive number for that. So positive times negative is negative. Positive divided by negative is negative. So it's a negative number. And that means it is a solution because we want the values that are less than or equal to 0. So these guys are part of our solution set. Solutions. And then we do the same thing. We're going to test something between 0 and 1. So let's test x equals positive 1/2. We do the same thing. So 1 minus 1/2 on the top. 1/2 times 1/2 plus 1/1. So this is going to be positive in the numerator still, because 1 minus 1/2 is still positive. 1/2 is now positive times positive. So positive, positive, positive. Everybody's positive. It's a happy group, but not part of our solutions because we want the negative numbers. And then we can test something bigger than 1. So maybe x equals 2. Now we have 1 minus 2 in the top over 2 times 2 plus 1. So 1 minus 2 is a negative number divided by positive times positive. So negative divided by positive is negative. So these are also solutions. So now we've reminded ourselves that we're going to include x equals 1 because that makes the numerator equal to 0, and we have an equal sign here. But we're not including the endpoints at the -1 and 0 because that gives us a 0 in the denominator, and you cannot divide by 0. Absolutely throw those ones out no matter what's going on. So our solution, our answer, is all the x values between -1 and 0. So everything that's bigger than -1 but less than 0, but not including those endpoints, union everybody that's bigger than 1, but we do want to include positive 1 because it makes our solution equal to 0. So that's our answer for that problem. It's a lot of work. Sorry, some problems are a lot of work. Okay, I think just one more problem. So x squared minus 2 over x minus 7. So this one, they've already done step 0 for us. So that's nice. They got 0 on one side. Step 0, check. Step 1, we need to find the zeros of the numerator and the denominator. So we have x squared minus 2 equals 0. So here you have to be careful because you might be tempted. So this is fine if you want to do x squared equals 2 and x equals square root of 2, but we have to remember that we get 2 answers from this, both plus square root of 2 and minus square root of 2. It's really important for this problem to do that. So it might help you to instead, right, or you can factor, or if it helps, you can use your difference of 2 squares, x minus square root of 2 and x plus square root of 2 equal to 0 to get to the same thing. But we do have both of those things are solutions. And then we also have to find the zeros of the denominator. So x minus 7 equals 0, x equals 7. So these are our breakpoints. And remember that, so again, we have, so if we had strictly less than 0, we wouldn't use any of these as actual solutions because we would be looking for strictly negative, not equal to 0. But the little bar down here means also equals 0 is possible. So the x equals plus or minus square root of 2, those ones will give us solutions. but x equals 7 is not in the domain. So again, when I set up my sign analysis for step 2, we put all 3 of these breakpoints on. So minus square root of 2 down here somewhere, and then there's 0, and then there's positive square root of 2, and then there's x equals 7. So I'm going to put in our break lines. And again, 7 is not in the domain. It gives us a 0 in the denominator. So I'm going to put an open hole. But the positive square root of 2 and the minus square root of 2, again, because we're allowing for equal to 0, these are going to be part of our solution set. So I'm going to notate it that way. And then we have 4 regions again. So we have x is less than minus square root of 2, or in interval notation, minus square root of 2, minus infinity to minus square root of 2. If you want, you can go ahead and use the bracket sign, because we've already recognized that minus square root of 2 is going to give us a solution. Then we have our next interval is here. That goes forever in that direction. The next interval is minus square root of 2 is less than x is less than positive square root of 2, or again, minus square root of 2 to positive square root of 2. And I'm just going to use the brackets again right away, because I already know that minus square root of 2 and positive square root of 2 are solutions. Our next possible interval here is minus square root of, positive square root of 2, sorry, less than x less than 7. Really, I should put my equal signs here too, right? Less than or equal to, less than or equal to, less than or equal to minus 2. Over here, so this is square bracket square root of 2, 7 parentheses this time, because I'm going to throw out the 7 no matter what, because I don't want zeros in my denominator ever. And this is x is bigger than 7. And again, we're not including 7. We're going to infinity. So those are the 4 regions that we're working with. We again want to test the thing we want to test is x squared minus 2 over x minus 7. Normally we're going to use a factored version, like this x minus square root of 2 times x plus square root of 2. In this case, it might actually be easier to work with x squared minus 2 directly. So I think I'm going to work with that one. So I'm going to test with this x squared minus 2 over x squared minus 2 over x minus 7 instead of the factored version with the square root of 2. I just think it'll be easier. So in this first region, something less than minus square root of 2. It doesn't matter, you can go way less. Maybe x is equal to minus 10. And then we're going to plug it in. So you have minus 10 squared minus 2 over minus 10 minus 7. So in the top, we have 100 minus 2, so that's definitely positive. And in the bottom, minus 10 minus 7 is negative. Positive divided by negative is a negative. And I do want the negatives, because this is less than 0, which is negative. So these are part of our solution. Then we go to the next region, minus square root of 2 to positive square root of 2, so I can test x equals 0. So we have 0 squared minus 2 over 0 minus 7. So that'll be negative divided by negative. Negative divided by negative is positive, so these are not part of our solution set. Something between square root of 2 and 7. How about x equals 5? So we have 5 squared minus 2 over 5 minus 7. So 25 minus 2, so this is positive divided by negative, which is negative. So these guys are part of our solution. And then finally, we'll test something like x equals 10. And we have, again, 10 squared minus 2 over 10 minus 7. This is positive over positive, which is positive. And again, we want the negative numbers, so not part of our solution. So our final answer, is minus infinity to minus square root of 2. Square bracket, again, because it gives us equal to 0 when we plug in x equals minus square root of 2. Union positive square root of 2 to 7. And we're not going to include the 7 because it gives us a 0 in the denominator, but we do want to include with a square bracket the positive square root of 2 and minus square root of 2. So that's our answer for that. And then finally, one last thing, just watch out with your inequality notation to make sure it makes sense. So as they said, like they're just pointing, the book is pointing out, oh, this doesn't make any sense. And one of our MW says, I'm confused. I believe we did this notation in high school, probably did. But here, minus x, what they're saying here is that if you have minus 2 is bigger than x is bigger than 2, you're saying this is the x values. This is saying the x values that are smaller than minus 2. Because remember, right, you can put your x and your minus 2 on either side of the inequality, but the pointy side of your inequality is the small side. So these are the x values smaller than minus 2, because x is on the pointy side of the minus 2, the closed side. But x is on the open side of this inequality. So this is saying x is bigger than 2, smaller than minus 2, and also bigger than 2. But there are no such x values. Right? You can't be both bigger than 2 and at the same time less than minus 2. It's not possible. You'd have to be both positive and negative at the same time. It's crazy. You can't do that, right? So there are no such x values, right? So it's just like that inequality just doesn't make any sense. If you wanted to write there are no solutions, you could do it in this way, in a very clever way, right? There are no such x values, so there are no such solutions. So you can't just group these things together. So instead, you really have to write them as two separate pieces, right? You have to write x is less than minus 2, and also the solutions where x is bigger than 2. Those are two different sets of numbers. You can't group them together like that. You can, if you had the solutions that were in the middle, right, you can write something like minus 2. So it doesn't make any sense. So you have to write instead x is less than minus 2 or x is bigger than 2 in order to describe the solution set here. We can have something like minus 2 less than x less than 2, which is not a solution to the above problem, but just another inequality. This inequality does have values that solve it, right? Because these are x values that are bigger than minus 2, but also less than positive 2. And there are plenty of them. There are infinitely many, 0 and 1 and minus 1 and 1/2 and 1/4 and pi over 2 and square root of 2. And there are infinitely many numbers in this range. So this is a valid range, but this one, which looks very similar, doesn't make any sense because there are no such x values. So that's what they're trying to get at with the notation. You just have to be careful. Okay, that's a lot of stuff. I'm going to post this video on Latte for you guys, and I hope it helps. And have a great day, everyone.